Welcome back to the Deep Dive. Today we're plunging into the incredibly promising world of solid-state batteries.
Yeah, it's a really exciting area.
Imagine a future where, your phone charges in minutes, your EV goes way further, and batteries are just inherently safer,
Yeah.
lasting for ages.
Exactly. That's the potential we're talking about: higher energy density, much longer lifespans, and a big jump in safety compared to what we have now.
It sounds transformative, but here's the twist, and it's almost mundane. A major hurdle seems to be something called lithium carbonate.
hmm
How can something, seemingly simple like that be the Achilles heel for such cutting-edge tech?
It's a great question. The issue is that lithium carbonate forms really, really quickly on a key material. It's called lithium lanthanum zirconium tantalum oxide.
Okay, that's a mouthful.
Yeah, let's just call it LLZTO. It's a crucial solid electrolyte, kind of like the highway for ions in the battery. And this reaction, lithium carbonate forming on its surface, it's a huge roadblock.
So how rapid is rapid,
Yeah.
in practical terms?
The research we're looking at today found a measurable layer can form in, get this, as little as 3 minutes of air exposure.
3 minutes. Seriously?
Yeah. Think about it. You step away for a coffee and your electrolyte is already starting to get contaminated. It just shows how pervasive this problem is.
Wow. Okay, so our mission today, understand this contamination, look at current fixes and why they maybe fall short, and then dive into this newer idea, open-air plasma treatment.
Right. We're tackling a fundamental chemistry problem here, not just, tweaking the engineering.
Before we get to the plasma, let's really unpack why this lithium carbonate is such a big deal. What does it actually do wrong inside the battery?
Okay, so the core issue is the LLZTO surface itself. It's naturally basic, chemically speaking.
Meaning it reacts easily with acids.
Exactly. Especially acidic gases like carbon dioxide, which is everywhere in the air, along with moisture. So LLZTO basically wants to grab CO2 from the air.
Ah, okay.
And that reaction forms lithium carbonate right on the surface. Remember, LLZTO is supposed to be this superhighway for lithium ions.
Yeah. Well, this lithium carbonate layer is like suddenly throwing up roadblocks and potholes all over it.
Right, so it doesn't just sit there nicely. It actually messes with the traffic flow, the ion flow.
Precisely. It dramatically increases what we call interface resistance. Think of it as friction at the boundary between the electrolyte and the electrodes.
And that means...
That means lower power output, slower charging, slower discharging. The ions just can't move freely back and forth like they need to. It's a major performance killer.
Okay, so it gums up the works at the surface. Does it cause trouble deeper inside the LLZTO too?
It can, yeah. It can hinder ion movement within the bulk material itself. So it's not just a surface traffic jam. It's like having slowdowns within the highway lanes too. It limits the overall efficiency.
And this is where it connects to something we've discussed before, something potentially dangerous. Dendrites, those little metal spikes. How does lithium carbonate lead to those? Right, this is the really critical safety part. Under certain conditions, especially if you're charging fast, that lithium carbonate layer can actually be chemically reduced.
Reduced, meaning it changes chemically.
Yeah, it can form lithium compounds that conduct electricity. And these compounds tend to collect in the grain boundaries of the LLZTO, like tiny cracks or seams between the crystals.
Okay.
And these conductive spots become nucleation sites, little starting points for lithium metal dendrites to begin growing.
Ah, I see.
And if those dendrites grow all the way through the electrolyte...
You get a short circuit.
Exactly, a short circuit, which can lead to thermal runaway. That's the fire or explosion risk everyone wants to avoid.
Definitely. Okay, so beyond the big safety risk, what are the more immediate things someone might notice? Like, how does it affect the battery day to day?
Well, you'd see the battery just not lasting as long. Its overall lifespan would be shorter, and its usable capacity would drop faster over time.
It degrades quicker.
Yeah, it's like building on a shaky foundation. Any instability at that crucial interface compromises long-term performance and reliability. So it hits performance, safety, and lifespan. A triple whammy.
Okay, so it's clearly a big multifaceted problem. What have people tried so far to fix it?
Well, there have been a few main approaches. One is pretty straightforward: mechanical polishing, basically physically scrubbing the lithium carbonate off.
Sounds difficult to do precisely and consistently on a massive scale.
It is very labor-intensive, not really practical for making millions of batteries.
Right. What else?
People have tried using inorganic additives, like putting thin coatings of things like lithium fluoride on the surface, trying to act as a barrier.
Does that work?
It can help, but it adds complexity. You have to control the coating very carefully, particle sizes, how well it mixes. It makes manufacturing trickier and potentially more expensive. Quality control becomes a bigger issue.
Okay, so polishing is tough. Additives are complex. What about heat? Thermal treatments.
Yeah, that's another route. Heating the LLZTO in a controlled environment, usually under an inert gas like argon, can help break down the lithium carbonate.
Inert gas meaning no oxygen, no CO2.
Exactly, to prevent it from just reforming. And it can be pretty effective. Heating at, say, 250 degrees Celsius for an hour might get you around a 70% reduction in that interface resistance.
That sounds pretty good.
And going even hotter, like 900 Celsius for an hour in argon, can get you over 99% reduction.
Wow. Okay, so why isn't everyone just doing that?
The catch is the controlled environment. You need expensive inert gas setups, vacuum chambers potentially, long processing times, specialized high-temperature equipment.
Ah, the scalability and cost problem again.
Precisely. It works in the lab, but making it work efficiently and cheaply for mass production is a whole different challenge. There are also things like rapid thermal pulses, but they tend to give less reduction.
So it feels like all these current methods, polishing, additives, thermal treatments, they work to some extent, but they all stumble when you think about making batteries affordably and at scale.
That's a fair summary, yeah. They all have significant limitations for real-world, high-volume manufacturing. We need something that's effective and scalable and cost-effective.
Which brings us finally to the potential game changer, open-air plasma treatment. Sounds cool, but what exactly is plasma? For those of us thinking, sci-fi movies or TVs.
Yeah. Think of it as the fourth state of matter. You've got solid, liquid, gas, and then plasma. It's basically a gas that's been energized so much superheated, usually that its atoms lose electrons and become ions.
So it's like a supercharged, highly reactive gas.
That's a great way to put it. It's full of ions and electrons and reactive neutral particles, making it great for surface treatments.
Okay, so how does this specific open-air plasma approach tackle the lithium carbonate? What makes it special?
There are a few key things. First, and this is huge, it works in open air at normal atmospheric pressure.
No vacuum chambers, no special argon gas tanks.
Exactly. That immediately slashes the cost and complexity compared to many other methods. It's a massive plus for scalability in manufacturing.
Okay, that's a big deal right there. What else?
Second, they use a specific type called a blown arc discharge. This creates what's known as a potential-free discharge.
Potential-free.
Yeah.
Meaning no strong electrical voltage right at the surface.
Right. Instead of relying on a strong current that could damage the sensitive LLZTO, which is an insulator, it uses this cloud of neutral but still highly reactive plasma particles for the cleaning. It's gentler.
Like using a chemical cleaner instead of sandblasting.
Kind of, yeah. It makes it much safer for delicate, non-conductive materials like LLZTO. This potential-free aspect is really important because many plasma systems need the material to be conductive. This opens the door to treating insulators effectively.
That versatility sounds crucial.
Yeah.
Okay, third key feature.
Tunability. They have really precise control over the plasma. They can adjust the gas temperature anywhere from near room temperature up to 1,500 degrees Celsius.
Wow, quite a range.
And they can control the intensity or flux of the plasma and even influence the types of reactive species it generates. This allows them to fine-tune the process to target the lithium carbonate specifically without wrecking the underlying LLZTO. It's like having a very precise cleaning tool.
Precision cleaning in open air. Okay, now, the study mentioned a custom metal shroud. What's that about?
The shroud. That's a clever piece of engineering. It basically fits around the plasma nozzle and the sample area.
Like a little protective bubble?
Pretty much. Its main job is to push the surrounding ambient air with all its moisture and CO2 out of the way during the treatment. It creates a localized controlled atmosphere right where the plasma is working.
So the plasma cleans the surface, and the shroud stops it from getting dirty again immediately from the air.
Exactly. It prevents that instant recontamination. It's like a mini clean room just for the treatment zone.
Makes sense? Does it do anything else?
Yes, there's a crucial cooling step afterward. Once the plasma treatment is done, they flow nitrogen gas through the shroud. This cools the sample down quickly, specifically below 400 degrees Celsius.
Why that temperature?
Because LLZTO gets fussy at higher temperatures. Above about 450 C, it starts absorbing CO2 more readily again. And above 600 C, the lithium ions themselves become too mobile, which can actually promote lithium carbonate reforming. So cooling it fast below 400 C helps lock in the clean surface.
Very smart. Okay, so that's the setup. How did they test it? What were the experiments like?
Right, so they first made the LLZTO pellets. They used a sol gel method. That's basically where you start with a colloidal solution that forms a gel, which you then process into the final ceramic material.
Okay, sol gel, got it.
Then they sintered these pellets to make them dense. And importantly, they deliberately exposed them to normal air for 2 days.
To make sure they got a nice even layer of the problem, the lithium carbonate.
Exactly,
Oh.
simulating what happens in a real-world scenario. Then they treated these contaminated pellets with the open-air plasma.
And how did they measure if it worked? What tools did they use?
They used a whole suite of techniques. For the surface chemistry, they used X-ray photoelectron spectroscopy, XPS. That's like a super detailed chemical fingerprint analysis for the very top layer, telling them exactly how much lithium carbonate was there versus other stuff.
Okay.
Then X-ray diffraction, XRD, to check the crystal structure of the main LLZTO material, making sure the plasma didn't damage it.
Important.
Laser imaging to look at the surface topography, how rough or smooth it was. And finally, the big one, electrochemical impedance spectroscopy, EIS.
That measures the battery performance stuff.
Yeah, that measures the interface resistance and how well ions can move the direct link to actual battery performance.
All right, the results? Drum roll. Did the open-air plasma actually remove the lithium carbonate?
Yes, it did. The short answer is it definitely worked. All the treatment times they tested, from 5 minutes up to 40 minutes, showed a reduction.
And what was the sweet spot?
The most significant reduction they highlighted was after 20 minutes of treatment using nitrogen as the ionization gas. They saw a 31% decrease in the XPS signal specifically for lithium carbonate.
31%. In 20 minutes.
Yeah.
In open air. How good is that, really? How does it compare?
Well, here's the interesting comparison they made. The level of cleaning they achieved after 20 minutes with this open-air plasma was comparable to the surface state you'd get just 3 minutes after cleaning it, with a much harsher, more complex vacuum-based argon ion sputtering method.
Whoa. So similar cleanliness, but without the vacuum chamber and all that hassle.
Exactly. That's the key takeaway from manufacturing potential. Achieving that level of clean in an open-air setup is a really big step.
That is impressive. Did it clean off other gunk, too? Other contaminants?
Yes. Interestingly, shorter treatments were actually better for some other things, like 5 or 10 minutes, significantly reduced adventitious carbon, just random carbon crud on the surface. They got a 70% reduction in that after just 5 minutes. Also good reduction in carbon-oxygen carbon type stuff.
So you might be able to tune the time depending on what exactly you're trying to clean off.
Potentially, yeah. It suggests some flexibility.
Now, what about the LLZTO itself? Did the plasma treatment damage the main structure?
Mostly good news there. The XRD tests showed that the main garnet crystal structure of the LLZTO held up really well. They didn't see significant formation of nasty secondary phases like pyrochlore, which kill conductivity.
Okay, that's crucial. But you said mostly good news.
Well, they did detect some minor impurity phases, things like lithium oxide, magnesium oxide, zirconium dioxide, and a couple of mixed magnesium-lithium tantalum oxides.
Where did those come from?
They suspect it might be contamination from the magnesium oxide crucible they used during synthesis. It's something to watch out for and optimize because even small amounts of impurities could potentially affect performance or long-term stability.
Right, something to refine. What about the surface smoothness? Did the plasma roughen it up?
Actually, the opposite. The laser imaging showed about a 36% reduction in surface roughness after the 20-minute treatment. So it seems to have a mild etching effect that actually makes the surface smoother on a fine scale.
Smoother. At a contact, maybe. Okay, so clean the surface, smoothed it, didn't wreck the main structure, but did it actually make the battery work better? What did the EIS tests show?
Ah, the ultimate test. And yes, a clear improvement. They measured the interface resistance on pellets where they treated just one side with the plasma.
On site. Look.
Even with just one side treated, the resistance dropped significantly. Untreated pellets had an interface resistance around 68 kiloohms,
Okay.
plasma-treated ones, around 37 kiloohms.
Wow, that's almost half. A reduction of about 44%.
Exactly, nearly cutting that interface resistance in half.
For the listener, what does cutting that resistance by almost 50% actually mean in terms of using a device?
It means ions move much more easily across that interface. So you'd expect significantly faster charging, the ability to deliver more power when needed, like accelerating an EV, and potentially a longer overall battery life because there's less resistance causing degradation. It makes the whole process much more efficient.
That's a tangible benefit, and you said that was only treating one side.
Right. Which suggests if you could treat both interfaces, especially in a thin film battery design where access is easier, the improvement could potentially be even greater. It points towards future optimization.
So putting it all together, while maybe some lab-based vacuum methods can get slightly higher percentage removal in the lab, this open-air plasma offers this compelling package deal. Pretty good cleaning, done quickly in open air without complex equipment. It sounds genuinely practical for manufacturing.
That's precisely the point. It demonstrates a viable pathway towards manufacturing solid-state batteries, or at least critical components, using simpler, cheaper open-air processes. That could be huge for accelerating adoption and getting these safer, higher-energy batteries into more applications.
That really is the bigger picture, isn't it? Moving from the lab to the factory floor. So what's next? Where does the research go from here?
Several key areas. One is long-term stability. How long does this clean surface stay clean after treatment under different conditions? Does the lithium carbonate creep back?
Good question.
Another is digging deeper into those minor impurity phases, understanding exactly how they form and finding ways to prevent them entirely.
Right, optimize the process.
And as we mentioned, applying this to thin film electrolytes is a big one. Those designs are crucial for next-gen batteries, maybe even anode-free batteries, and plasma treatment could be ideal for treating those delicate layers.
Lots still to explore, but it sounds like a really promising direction.
Definitely. It tackles a fundamental, persistent problem with a solution that seems genuinely scalable and practical. That's often the key to unlocking a new technology.
It's incredible, really, how something as basic as air exposure creates this headache, and then a sophisticated tech like plasma, applied cleverly, might be the answer. It shows that link between deep materials science and smart engineering.
Absolutely. And it makes you wonder, this plasma tech is pretty adaptable. So a question for you listening. What other tricky material surface problems, maybe in totally different fields, do you think could benefit from this kind of targeted open-air plasma treatment?
That's a great thought to leave folks with. We'd love to hear your ideas. Thanks for joining us on this deep dive into open-air plasma and the fascinating future of solid-state batteries.